Okay, so now we'll look at Einstein's problem. So Einstein's problem revolved around how to demonstrate that total energy was conserved within his new theory of gravity, known as the general theory of relativity. With Einstein's new equation, they could not find where this energy was accounted for. So Einstein's problem. Then a mathematician, David Hilbert, attempted to find these energy conservation equations in Einstein's theory, but only found the Bianchi identities. These identities showed energy conservation only in a completely empty universe, making them seem useless for a universe like ours that is filled with matter. Okay, I think so. Someone new has also joined. So thank you for joining us. So if you have any questions, you can raise your hand and ask us. So Emmy Noether. So she later realized that Einstein's proposed conservation equations contained a pseudo tensor, meaning it does not remain the same quantity in different frames. Meaning, like if we see that there is some energy in one frame, it will disappear in the other. So this implied that the gravitational energy observed in one frame could completely disappear in another, which Noether believed was a fundamental mistake that disregarded the foundational principles of general relativity. Symmetry. So symmetry is any action you can take that leaves an object unchanged. Triangle symmetry, an equilateral triangle, has three axes of symmetry where reflections leave the triangle unchanged. It also has rotational symmetries, meaning it looks the same after rotations of 120, 240 or 360 degrees. So so a symmetry, as explained, is any action that we can take that leaves an object unchanged. So it also applies for mathematical functions. If we shift a mathematical function up or down by a constant amount, it does not change its derivative. This is referred to as continuous translation symmetry because it can be shifted by any specific amount and the derivative remains the same. This shift can be by any amount, not just fixed values like the rotations of a triangle. So the derivatives or the function remain unchanged even after we add some constants. So so time translation. So translation symmetry is a type of symmetry where an object or system remains unchanged after being shifted or by being moved to another position. So what does that mean? Let's take an example. In an empty static universe, there is nothing special about any particular point. This law of physics, the laws of physics are the same everywhere, meaning the universe is completely uh, symmetric under translation in space. This spatial translation symmetry directly leads to the conservation of momentum, implying that an object thrown in the universe would continue indefinitely at the same speed. So it is like if there is a ball in an empty static universe and if we throw it, let's say it moved at 100 meters. So what we can do is that we can move the whole universe by 100 meters so that the object will remain unchanged. And for the rotational also, if we spin an object, let's say by 60 degrees, what we can do is that we can rotate the whole universe by 60 degrees so that it will be unchanged. So there's one more thing called principle of equivalence. So it states that if you are stuck in a rocket in outer space accelerating at 9.8 meters per square, it would exactly feel the same as if you were standing on the surface of the earth. So it was Einstein's happiest thought, imagining a window cleaner falling off a building. He realized that while the man would feel weightless and anything he dropped would remain stationary to him, this would be just as if he was floating in outer space. This led Einstein to understand that there must be an equivalence between accelerated motion and the action of gravity. This was significant because if he could understand accelerating frames, he would have a more general theory but also a new theory of gravity. So that is the general in general relativity. So it is the action between two accelerated frames. So there's one more thing called general covariance. So it is a very core tenet of general relativity. It is the idea where the laws of gravity must have the same form everywhere, no matter how we are moving. Einstein needed to use the tensors to satisfy this principle because then they should remain the same quantity regardless of the coordinate systems that are used to describe them. This property ensures that laws of physics look the same everywhere even when transforming points of spacetime. So initials so Einstein's initial proposed energy conservation equation for general relativity failed because it disregarded the foundational principle of general relativity, general covariance. Einstein proposed that if the energy of matter and the energy of the gravitational fields were added together, the total would remain constant. Noether discovered that the Einstein's equation contained a pseudo-tensor. This meant that when you tried to transform it from one frame of reference to another, it would not remain the same quantity anymore, which meant that gravitational energy discovered in one frame may completely disappear in another. So to understand what is a tensor, we have to understand what is a vector. So these are simpler examples to introduce tensors. A vector can be written with components that change if you use a different coordinate system. However, the underlying physical quantities, the vector itself remains the same because the components adjust in a complementary way. Tensors extended this idea by having more components often arranged like a matrix. Okay, how symmetry gives rise to conservation laws. So Aryan, can you read this slide? Hello Aryan. Hello Aryan, are you here? Okay, so in an empty universe, there's nothing special about any particular point. The laws of physics are the same everywhere, meaning the universe is completely symmetric under translation in space. This spatial translation symmetry directly leads to the conservation of momentum, implying that an object thrown in this universe would continue indefinitely at the same speed. So what does this mean? If we have an empty universe which is not moving and static, and if we throw an object like a ball in here and it says, let's say that it travels 100 meters, what we can do is that we can move the whole universe by 100 meters. What would that lead to? It would lead to the conservation of energy or translation symmetry, which directly gives rise to conservation laws, which means that if we throw that object, it would continue indefinitely at the same speed. And conservation of momentum too. If we spin an object here by let's say 60 degrees, what we can do is by that we can move the whole universe by 60 degrees so that the whole universe remains unchanged. So by considering a time translation symmetry, that the laws of physics are the same at slightly different times. Noether was able to manipulate the Lagrangian with the action framework through a series of mathematical steps. She showed that if the Lagrangian remained unchanged under a specific time shift, then a specific quantities, which turns out to be half mv squared plus v, representing the total energy, has a time derivative equal to 0. This meant that the total energy had to be constant in essence. So the principle of least action also allowed Noether to mathematically derive that time translation symmetry is equivalent to the conservation of energy, thus revealing the fundamental origin of this conservation law. The problem. So Einstein's initial proposed energy conservation equation for general relativity failed because it disregarded the foundational principles of general relativity, general covariance. Einstein proposed that if the energy of matter and the energy of the gravitational fields were added together, their total would remain constant. Noether discovered that Einstein's equation contained a pseudo tensor, which meant that when you tried to transform it from one frame of reference, it would not remain the same quantity. So the gravitational energy observed in one frame could completely disappear in another. So, and what is a tensor? So, to explain tensors, we have to first understand a vector. So, an vector, we can say it remains same if we draw a triangle, and if we change or shift to another coordinate systems, let's say that the triangle gets on to 3 blocks, and if we change the coordinate system so that the previous block will maybe like become 2 blocks, so the the quantity will become 6, but the physical system will not change. Its component will adjust in a complementary way. So in tensor is like a much more advanced form of a vector. So this it has way more components than in vector. So it is a more complex vector, and I think so we'll discuss about tensors about at some other presentations. It's a pretty vast topic, the tensors and vectors. So this pseudo tensor meant that when we change the whole coordinate system, what will happen? That the object will not remain the same. So are you satisfied? Okay. Okay, so by considering a time translation symmetry that the laws of physics are same at slightly different times, Noether was able to manipulate the Lagrangian with the action framework through a series of mathematical steps. She showed that if the Lagrangian remains unchanged under the time shift, then a specific quantity, which represents the whole uh, specific whole energy, the total energy, has a time derivative which equals to 0. This meant that the total energy had to be constant in essence. So the principle of least action allowed Noether to mathematically derive that time translation symmetry is equivalent to the conservation of energy, thus revealing the fundamental origin of this conservation law. So Lagrangian and this uh, what we say that this principle of least action, these are way advanced topics, and I've just used it, and I may not be able to like give something. So uh, let me just give an example. We'll assume that there is a pipe, and the first term in this equation, which is also called the continuity equation, is how the amount of water within a section, with a specific section of the pipe, changes. So how much, the first term will represent how the water changes within a specific section of the pipe, and the second term represents the difference between the water flowing out and the water that is flowing in. So when these terms meet, it means that they are being cancelled to zero. It means that the total amount of water in that specific section only changes. Water flows in or out, not because it is being created or being destroyed within the section. So if we look at it at a very universal scale, what would that be? So we can say that the first term in this equation will represent how the amount of energy will change within that specific section of the universe or the space time. So the pipes are being replaced by space time, and the water is replaced by energy. And the second term of the equation will represent the difference between the energy flowing in and energy flowing out of that specific section of a space time. And when these two meet, they cancel to the zero. So that would be conservation of energy, but that is not the case. uh, in in the universal time scale, we also consider the curvature of space time. So that would be like, there are leaks and it is bent, the pipe is bent and there are leaks happening, so that the energy is not being conserved. And if you have to get a equation for the and specific section of space time, what we have to do is to add the is that we take the first and the second term, and we also add the curvature of space time. So this is like, I just gave an example of the Lagrangian that Amin author used to say that time translation symmetry is equals to the conservation of energy. So that is how symmetry gives rises to conservation laws. So, and our universe, it does not have that perfect time translation symmetry, meaning over large time scales. Astronomers have observed that the universe is not only expanding, but it is also speeding up. So this expansion means that the universe is not same as now it was billions of years ago, and it will be different from billions of years ago from now on. So therefore, over a very large time scale, the universe is not symmetric in time. Since time translation symmetry is linked to the conservation of energy, this means without this symmetry, our universe does not have the conservation of energy. So this means that large scales means that energy, as we usually think of, is not conserved. For example, a photon traveling through the expanding universe, it loses energy. So so as it moves through the universe, its wavelengths get stretched because the universe is expanding, and which means that it has a lower wavelength, which corresponds that it lost energy. But where did that energy go? It just simply ceases to exist. And this is how the general relativity loophole was just solved. Our universe. So our universe does not have perfect time translation symmetry, or in large time scales. Astronomers have observed that the universe is not only expanding, but its expansion is also speeding up. This means that the universe is not same as now as it was billions of years ago, and it will be different billions of years from now. Therefore, over large time scales, the universe is not symmetric in time. Since time translation is linked to the conservation of energy, the absence of this symmetry on large scales means that the energy, as we usually think of, is not conserved in a universe. For example, a photon traveling through the expanding universe loses energy. So it means that our universe does not follow these laws. But how, like in lab, how do we see that these laws are being followed? So there was one more thing that we had covered, general covariance, which meant that the laws of gravity must be same in the have must have the same form in every frame of reference, no matter what and where we are. So this, in the context of general relativity, it is an local symmetry, referring that the laws of physics will remain same uh, in any region of space-time, regardless of how are we moving or a specific frame of reference. It implies that in any small region, you can change your frame of reference or transform the points of space-time as much as we like, and the physical laws will remain consistent. So okay, so do we have any questions? uh, Sir, do you have any questions? Okay. Sir, do you have any questions?
Please,
Okay. So, in this presentation, we discussed about the conservation of laws, about those four conservation of laws, and how Einstein faced the problem, the general relativity loophole, where we thought that the universe is not obeying the laws of conservation. So, then a mathematician David Hilbert came and said that it may be wrong because of the Bianchi identities, which said that the energy would be conserved in an empty static universe. So then another physicist came, Emmy Noether, which then used symmetries to say that symmetries give rise to conservation laws, and our universe does not have time translation symmetry, which meant that our universe does not follow these laws. So the reason that we are seeing that these laws are being followed is because of general covariance. It is in local symmetry, and because of that we are seeing in our small specific framework that these laws will remain consistent. So thank you for joining everyone.